Okay. Okay, so now I can hear you better. And let me start to share my screen with you all. Okay. 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 Let's come back. Slides. Okay. Today we will finish this diagnostic horizons, specifically about the surface diagnostic horizons. Okay. We talked about the folic and histamic horizons that are organic diagnostic horizons. They are formed essentially by organic carbon. So they present dark colors, a low density, and a high content of organic carbon. We also describe these horizons that are related to human mixing of soil, mixing with vegetable, organic, mineral materials, okay? We also describe these three horizons that are mineral horizons. And these mineral horizons present a low content of organic carbon in comparison with these two organic horizons, but they also present dark colors. These two are related to a high pH and a high content of calcium and a high content of calcium carbonate, especially calcium carbonate. And this horizon is associated to a low pH and a high content of aluminum and hydrogen. Okay. And now we have to talk about these three surface diagnostic horizons. They have a specific property in common that these two horizons, they could be surface or subsurface horizons. So we can find them in the surface or in subsurface, okay? And they are related to locations, to areas that have a dry climate, that present a higher evapotranspiration than precipitation. So the quantity of water that's loose by evapotranspiration, it's higher than the quantity of water that fall down by precipitation. And this favor the concentration of salts in the surface or in the subsurface or in the surface and subsurface horizons, okay? And they form these two specific diagnostic horizons. Again, they could be related to surface or subsurface horizons, okay? And this one, the Pimpake horizon, is a horizon that was formed in the surface, but now it is buried. Now we can see other horizons that present an overlaying layer above this horizon. So it was formed in the surface, but now it is in the subsurface. Okay, we'll discuss about that. Don't worry. So I just need to this horizons. Okay, Malik and Jernik and Amrik. Okay. And And now we have the gypsic horizon. The gypsic horizon is, as I said, a surface or a subsurface horizon. So we can describe it in the surface, or like in this picture, we can see in the subsurface. And the gypsic horizon is a horizon that's related to accumulation of secondary gypsum. So gypsum, it's a salt of calcium and sulfite, and this salt can be described, it can be seen in soils that present a dry climate or dry conditions. So the evapotranspiration is higher than precipitation, and this induces favor the concentration of salts, especially calcium sulfate in the subsurface. Okay, the sulfate of calcium, we can see its concentration in the subsurface or in surface horizons and form the gypsic horizon. The gypsic horizon, it's a non-cemented horizon, so we can easily use a knife to take some pieces of this material, so it's soft or present a hard consistence, but it's not too hard, so we can easily broke it with a knife or something like that. Tool, okay, it's not so hard, it's not cemented horizon. So we can see voids with water and or air inside these horizons, not all fulfilled by salts, okay? How this horizon could be formed? It's very easily. When we have an arid or a semi-arid climate, we can see that we have a low rainfall regime, so the rain is not so strong, and the soils favor the infiltration of water. Some part of this water will penetrate, and they generally present rocks very close to the surface. So they are not so deep or thick horizons and layers, but we easily can find the rocks. And when water found the rock, the water start to accumulate in the zone, and water accumulate in the zone, it starts the weathering of the rocks. So these rocks, this R layer, start to lose some elements by the weathering of its minerals. So feldspar, plagioclase, biotite, muscovite, they start to lose some elements like calcium, magnesium, potassium, and sodium. They start to release from the rock to the water, and this water gets a high concentration of these elements. And when we have the dry season, when we have a drought, or when the rainfall stops, we have something like this: a rock with water in the subsurface, and now we have the sun here, and here we have a lot of radiation, sunlight, that increase the temperature of the soil, and now water start to migrate from the subsurface to the surface. And this water brings these elements, this calcium, magnesium, and other elements from the subsurface to the surface. And when water start to evaporate, start to change its phase, we now have a concentration of sulfate calcium in the soil. So we start to create a layer with a lot of sulfite and calcium. It could occur in the surface where we found higher temperatures, the highest temperatures, or it also can be found at subsurface. We generally found it in the surface, but we also can find it in subsurface. Okay, so we create a horizon that's present a high content of sulfate calcium, because the sulfate calcium start to precipitate by a water that present a high content of elements. And this water present a high content of elements because we have a dry climate and rocks very close to the surface. Okay, we can see this kind of horizon in wet climates. So if you're looking for a rainforest or soil in a rainforest, we can't find this kind of horizon because the weather is too wet. We have a lot of rain, and we can also have higher temperatures, but we have a lot of rain. So water start to leaching of these elements, and water don't migrate from the subsurface to the surface, bringing elements. Water, it's always going down and leaching the elements. So we can't create this kind of horizon in wet climates, okay? Only in arid or semi-arid regions. This picture is very good because we can see a lot of needles. Oh, I'm sorry, needles. A lot of needles of sulfate calcium, okay? They are formed in dry conditions. And this gypsic horizon is a horizon that presents a mineral material, and this mineral material present a low organic carbon. So the organic carbon is lower than 20%, okay? We have at least 5% of gypsum in the fine earth. So we can see in this horizon a high content of sulfate, okay, a calcium sulfate here. And we need also this or these conditions. We need to find at least 1% of gypsum in the surface of the materials. The protogypsic properties. So we have to see at least 1% of gypsum in the soil surface, okay? Or we have to find at least 5% or higher content of gypsum in the horizon when we compare with the material below. So this horizon, this gypsic horizon, should present at least 5% of gypsum more than this horizon, the sea or the horizon below, okay? So we need to present a higher concentration, at least 5% of gypsum here, calcium sulfate. And we need to find a product between the thickness of this horizon and the gypsum content of at least 150. So we calculate a ratio between the thickness of this material and the gypsum content, we need to find at least 150. Okay, so show us that we have a high content, a high accumulation of gypsum in a specific thickness. And how higher is this thickness, we also should present a high content of gypsum. Okay, this horizon does not form part of a petrogypsic horizon. A petrogypsic horizon, it's cemented horizon. Oh, just a moment, someone is asking to enter in this class. Okay. So this horizon, as I said, it's not cemented. Okay, so the gypsic horizon presents a high content of gypsum, but it's not cemented. It's not a part of the petrogypsic horizon, a cemented horizon. And the gypsic horizon presents at least 15 centimeters of thickness. Okay, so these are all the diagnostic properties, the diagnostic criteria that we should follow to identify a gypsic horizon. Horizon that's essentially formed in arid and semi-arid regions. We can also find the Salek horizon. The Salek horizon, it's very similar to gypsic, but in this case, we can see other salts than calcium sulfate, okay? So we can see a high content of other salts, and it is also formed in dry and semi-arid regions, in arid and semi-arid regions, because the same process, we have the concentration of these materials in the surface or the subsurface. So we concentrate salt because water is being releasing by evapotranspiration, because the precipitation is too low in comparison to evapotranspiration. The temperature is very high, and we concentrate salts in surface or subsurface. Okay, here we can see some pictures that show us here in the surface this white color. Okay, and here we can see some white dots. Okay, these white dots show us a concentration of salts in the soil. Okay, and form a salt horizon, Salek horizon. Okay, Salek horizon should present a high pH. Okay, because the high content of salts increase the pH, so we should present at least 8.5. It's a very high pH, it's alkaline pH. We also should present a high electric conductivity, because the high content of salts increase the electric conductivity. Okay, so we should present a high electric conductivity in these horizons. Okay, and it should present at least 15 centimeters of thickness. Okay, so it's a soil that presents a high pH, a high electric conductivity, and present at least 15 centimeters of thickness. It's also formed in arid and semi-arid regions by the concentration of salts in surface or subsurface horizons. Okay. And the last one is the Pompeiic horizon. That is a horizon that's formed in the surface but now it is buried by an overlaying horizon, okay? So its format in the surface was in the past an A horizon, but now this A horizon is buried. Like in this picture, we can see this dark color here, and this dark color show us that this horizon could be related to a horizon. And this material is just overlaying this ancient A horizon. So in the past, soil surface was here, and some erosional process bring all this material and cementate all this material over this horizon, this A horizon. So create this Pompeic horizon. It's a horizon that's formed by erosion or geological process that induce the overlaying of an ancient A horizon. Okay? So it's a typical A horizon that was formed in the past, but now is buried. Like in this picture too, we can see here, it's not too dark, it's not so dark like in the last picture, but we can easily see here a darker color than even in the surface horizon, or here this thin layer, or here. So show us that in the past, the soil surface is here, and something happened, an erosional process bring this material, and all this material, it's now overlaying an ancient A horizon. And this A horizon, it's a Pompeic horizon. Okay? So it's only formed by burial process. The Pompeic horizon also presents some criteria that should be followed. Okay, it's a mineral material, so the organic carbon it's lower than 20%. Okay, it should present at least 0.2% of our soil organic carbon. So the organic carbon content it's lower than 20, but should be equal or higher than 0.2. The content of organic carbon, it's at least 25% in relative terms and 0.2% in absolute terms, higher than the overlaying layer. So it should present a higher content in comparison to the overlying layer. We should present a lithic discontinuity. So we should present here something like the Pompeic horizons here. We should present some horizons or layers that are formed by a specific different material from this one. So here we have horizons that are formed from gneiss, and here we have some horizons that formed from sandstones. So we have a same soil profile that present different lithological materials, different parent materials. So we have a lithic discontinuity. So we have, for example, here on A horizon, here B horizon, and here 2A B horizon, a Pompeic horizon that's related to a lithic discontinuity. It's why we use this number 2 here, and we have the letter B because it's a buried horizon. So all the Pompeic horizons should are related to a difference of material from this horizon, and all these horizons. Okay, should show us any kind of difference that we can see that this material was formed in other region and was just eroded and the material was deposited here. Okay, and we have a thickness of at least 5 centimeters. Okay, so we have these materials that are related to a material that was buried. Like in this note, we can see some Pompeii horizons that follow these definitions, but in this case, it should present the lithic discontinuity, okay? Should also present some material that buried this ancient A horizon. Okay, so now we saw all the surface diagnostic horizons. Again, we have these two that are related to a high content of organic carbon. They are organic horizons. We have the 6 related to human-made horizons. They are formed by men by the mixing of materials. We have these 3 horizons that present a moderate to high organic carbon content. These 2 are related to a high pH and high content of calcium carbonate. And we have this one that's related to a low pH and a high content of acids. We have these 2 that are related to a high content of salts, and this a buried horizon. So they are very different between them. Very, very different. It's quite easily to identify these differences. Okay? Now, I sent you in the last class exercise with 2 questions, and I asked you to classify those horizons. Did you done the exercise? Can we try to classify these horizons?
JJ, I tried, but I'm not sure because the features you presented there are quite confusing.
Okay, okay. Anyone find some answer? Anyone could classify these horizons?
I also try to classify it, but I'm not sure also. But I got
Mhm.
some clue from the question from the classes, so I try
Okay,
to class it based on my understanding.
okay, okay. Okay, we can do this right now. It's not a problem. Okay.
Your screen is not showing.
Oh, I'm not sharing my screen.
I think it's having a black background.
Okay, it's because my background in Word it's black, but you can see the letters. Can you see the letters?
For me, no.
No. Let me
But
try.
from the previous,
And now,
okay, better.
can you see it?
Yeah, it's fine now.
Yes.
Okay, okay. So let's start. This surface horizon present 25 centimeters. Okay. It presents a red or yellow color.
Color.
Which color is that? Red or yellow?
Yellow.
No, it's red. We have a color that presents 2.5 of yellow and 7.5 of red. Let's see this color. Here is the muscle color chart, and let me find. Just a moment. Okay. Okay, it's 10. Oh, sorry. Let me just and my right hand. Okay. It's 10R. Okay. And 10R, it's a lot of red. And we have here 2.5 YR. So we have a lot of red colors. Just like here. And the color present just okay. The color present 3 and 3 of value and 3 of chroma. So it's something like here 3 and 3. So the color is here. Okay, this is the color of our surface horizon. And we can see in the other page the name of this color. I can see here. Okay. The hue is 2.5 YR. It's the right hue. And now 3 and 3 is a dark reddish brown color. Okay, so it's a reddish color. We have a lot of red, but it's a dark reddish brown color. Okay, so we can see the color of this surface horizon here. Okay, it's not a light color, it's not so dark, but it's a brown color, dark brown color. Okay, now we come back to the page and we can see a moderate grade, so it's not so strong, but it's not weak. And we have fine granular structures. So we have this spheric structures and the size is fine, it's not too big, okay? The consistency of the material is slightly hard when dry, friable when wet or when moist, and non-plastic and non-stick when wet, when the material is wet, okay? We have a high quantity of voids, dendritic and tubular voids, and these voids are abundant and present a size that's fine and medium, okay? So we have a very good description of this horizon and this data that present us some information, some precious information, okay? Let me just try to correct this table. So,
Okay.
just a moment. Okay, it's better now. Okay. So we are seeing only the data, okay? And the pH of this material is not so high, but it's not so low too. It's 5.8. 5.8, it's a very important pH because a pH equal or higher than 5.6, 5.8, we can't find aluminum. And aluminum is toxic for the majority of organisms in the earth. So we can find a very good pH to growing, okay? We can see a high content of phosphorus. This content 132, it's very high. We usually found phosphorus below 10 milligrams per kilogram or per decimeter. So it's a high quantity of phosphorus, okay? And the content of phosphorus, it's low. The potassium is low, I'm sorry. We can find a high content of calcium and magnesium, but especially to calcium, the content is very high. And we can find a low content of hydrogen. So the acidity of the soil is very low, but the pH is not so high, okay? And here we can see in this V value, we can see the percentage that's fulfilled by bases, by nutrients. So in this case, the content of potassium, sodium, calcium, and magnesium fulfill 83% of the cationic exchange capacity. So we have a high content of this material that's fulfilled by nutrients in the surface horizon. This is very good. Means that this horizon presents a high fertility, okay? And here we have the content of soil organic matter. That's 2.6. It's not so high. It's not too low, but it's not so high too. And here we have the content of the coarse sand, the fine sand, the silt, and the clay. So let's try to classify this diagnostic horizon using all this information, using the morphological information description, and using all this data. Okay, so let's see. Oh.
Okay.
The folic horizon, we know that we should present a high content of organic carbon to identify a folic horizon. In this case, we have only 2.6 of soil organic matter. Soil organic matter is not the same of organic carbon, so we have to calculate the content of organic carbon in this case. Let's do it. It's very easy. To find the content of organic carbon in a horizon, we just need to calculate a ratio between the soil organic matter and a factor of 1.724. So if I calculate a ratio between the soil organic matter and this number, I can find the content of organic carbon. So in this case, we have 2.66 percent of organic carbon, and we should calculate this ratio. Let's do it. Just a moment. Okay. So 2.66.
1.5.
We have only 1.5% of organic carbon. So in this case, it's not high enough to identify a folic horizon. So it is not a folic horizon in this case. We can say the same to histic horizon because it also needs a high content of organic carbon. Do you remember? At least 20%. So it's not a histic horizon too. An uncratic horizon. It's a fluted horizon, so it should present mottles and gray colors. In this case, the horizon presents a red color, so it doesn't present gray colors, and is not the dendritic horizon, right?
Yes.
It's not it. Okay, the Arctic horizon. Arctic horizon is a horizon that's formed by deep cultivation, intense addition of material, organic and mineral materials by humans. So in this case, we can see that it represents a value and a crown at least 3 should be equal or lower than 3. In this case, we can see that we are 3 and 3, so we are following. Okay, good. Oh, no. And we should present at least 1% of soil organic carbon, and we know that we have 1.5, so we also followed. Checked. Now, we should present a high content of phosphorus because the addition of the increase of phosphorus by human activity. In this case, we can see here 132. So we present a high content of phosphorus. So we also check this. We should present a high base saturation because humans try to increase the fertility of the soil. So we should present at least half of the cationic exchange capacity fulfilled by bases. In this case, we have 83%. So we have so much more than the half of CEC fulfilled by bases. So again, checked. And we should present a thickness of at least 20 centimeters. And we have soil horizon, that presents 25 centimeters. So our horizon is following all the criteria to identify a Arctic horizon. So this first example, this first exercise is a Arctic horizon, okay? Because this horizon fulfill all these criteria, follow all the criteria to identify the Arctic horizon, okay?
Okay.
Mhm. If I can make a suggestion to you, you should
Okay.
always follow this order that I insert here, trying to identify the surface diagnostic horizons. If you follow this order, you can easily classify every surface horizon, every diagnostic horizon, okay? Just follow this order because we have some specific soil properties that could be present in more than one. So if you follow this, you can easily identify any surface diagnostic horizon, okay? Let's
Okay.
see
Yeah,
this step.
sorry. I
I'm
have a
sorry.
question.
Okay.
Okay. I actually said pelagic to this first
Pelagic.
one.
Why?
Actually, because of the color, it has a low value of color white. It was actually the color that I was looking at. I didn't check other base
Mhm.
saturation, but now I've seen that pelagic has a base saturation of less than 50%.
Yes. So it's not a pelagic horizon. Okay. So if you just need to remember that you have to follow all these criteria when we have and in this case, we have to present a low base saturation. Okay.
Okay, because I checked the pelagic also has a high content of phosphorus one.
Yes, in this case,
And
yes. But
then the thickness is also up to
yes.
20. Yeah.
Mhm.
But it's just the base saturation that ruled it out from the description.
Yes. And we need to follow all the criteria. So if you have just one, okay, it's an other diagnostic horizon. Okay. But very good. Means that you are thinking and trying to understand very well. So it's good. It's not a bad mistake because you are following the criterias and how can we found all the information. So it's why I always said to you that you didn't need to record all the information because it's a lot of information, but you need to know how to see and look for this data in tables and descriptions. Okay, but it's very good. It's very good. Let's see the other exercise here. The second, it's easier. Okay, the second one, in this case, we have a horizon that present 35 centimeters, and the color is quite strange. We have an N, and this letter is to neutral. It's to gray colors. So this horizon present gray colors. Okay. In this case, we have a gray color, a content of clay that's not too high. We have, oh, I forgot to translate this, but this is sand and this is clay, I'm sorry. But we have a sand clay lawn texture. Structure is strong, so we have a strong grade. We have a granular type, granular shape, and the size is medium. And we have structure that's very hard when dry, it's firm when moist, and slightly plastic and slightly stick when moist. Okay. In this case, we have a low pH. It's a low pH. It's very acid, maybe acidic or extremely acidic. Okay. And we have a high content of organic carbon. It's very high. And we have here a high content of aluminum. And we present a low content of nutrients. So the potassium, sodium, calcium, and magnesium is very low. It's very, very low. The quantity of hydrogen is very high. So we have a lot of acid and we don't have a lot of nutrients, a lot of bases. Okay, so let's check which horizon present this soil properties. Okay. So let's start. The folic horizon, we should present at least 20% of organic carbon, and we only present 18%. So it's not a folic and it's not a histic horizon. Again, we just forget these two first surface diagnostic horizons because we don't present a content, a minimal content of organic carbon in these cases. We have the dendritic horizon. Okay, the dendritic horizon could be very good option because we present this gray color. Oh, let me show you the gray color of this horizon. It's here. And okay, it's here. Here is the color of this horizon. It's very dark horizon. It should present a high content of organic carbon, and it presents a high content of organic carbon. Okay. And so let's see, the dendritic, we should present at least these materials low value and low chroma, and we follow this. We should present a plated structure or massive structure, and we shouldn't follow this criteria because we present a granular structure. Let me see, granular structure. So it is not the dendritic. Okay. Just the hortic horizon should present a high base saturation. And in this case, I could calculate, it's quite easy to calculate this. Let me show you. How can I do this? No. Okay. Put this here. And let me increase the size of this so I could not too high. No. Yes, perfect. Okay. Okay. So let's calculate the base saturation. Okay. Base saturation, it's V%. And how could we calculate the V%? First of all, we should calculate the sum of bases. So we just need to sum these values. We should present the sum of calcium, magnesium, potassium, and sodium. Okay, in this case, we have, let me calculate this, just a moment, is 0.44 plus 0.0604 and 1. We have only 145. It's not a high content of bases. And we should calculate now the CEC, the cationic exchange.
I'm taking basis on 1.9 and not 1.45. So
Oh, yes, yes, because he's one.
yeah.
Okay. Yes, I'm sorry. I forgot to include, let me put it again so everyone could understand where I mistake. So 0.44 plus 0.06 plus 1 and plus
0.4.
Yes, thank you. So it's 0.9. So I need to include all these nutrients, okay? And now I need to calculate the CEC, the cationic exchange capacity. That it's the sum of bases plus this quantity of aluminum and hydrogen. And the CEC, it's equal 1.9 plus 5.5. So, of course, we have a huge value here.
This is not showing on the screen.
I'm not sharing my screen with you.
Better now.
Let me see, just a moment. No, I'm sharing my screen.
I see it's better now. I can see.
Okay,
yes.
okay. Yes, okay, okay. So, okay, so it's fit 7.4. Okay, and now we could calculate the base saturation using the sum of bases radial by the C is C, and just multiply by 100%. So it's 1.9 and 57 and 4, and we should only multiply this by 100%. So, of course, it's not a high number. And just multiply. It's just 3%. So the base saturation, it's only 3%. So it's very low. And so on is not a Arctic horizon because didn't follow this high base saturation. The Ihigric horizon is a horizon formed by irrigation and should present difference of texture between the horizons. So should present a higher content of fine materials. We couldn't identify this horizon using only one horizon. We should present the data, the texture of the overlaying material. So in this exercise, we couldn't say if this horizon follow all these criteria. So we just skip this horizon in this case because we don't have the data of the overlaying horizon, okay? Just in this case, but if we have the data of the other horizons, we just need to compare the content of the fine materials and in the surface and subsurface materials, okay? The pelagic horizon is a mixture of organic materials with a high content of organic carbon and presents a low base saturation. So maybe it's a pelagic horizon. Let us see. In this case, we should present a texture that's sand, loam sand, sand alone, or loam, or a combination of 10. In this case, we present a texture that is sand, clay, lawn. So if we look to the texture, we didn't follow this. And we don't follow other material, other criterias. I think that, let me see, we have the content of phosphorus here. No, I didn't include it, but if I include it, we could check if it presents this high content of phosphorus. I know because I classified this horizon in the past and it didn't present this higher content, okay? But it didn't present this texture, so it's not a pelagic horizon. A pelagic horizon is a horizon that should present artifacts, coal, bonds, charcoal, and kind of materials that wasn't added by humans. And the description of this horizon didn't mention anything like that. Didn't mention charcoal or ash or bonds. So I know that's not a pelagic horizon too. So a thermic horizon should be a mixture of materials, mineral materials, forming this kind of terraces, okay? In this case, should present any evidence of addition of material. And in the morphological description, we can't see anything about this. We don't have any evidence of adding of material. We don't have this information here. So if we don't have this information, it's because we don't have this adding. So it's not a thermic horizon, okay? Molic horizon should present a strong grade, and we have strong grades. We should present a dark color, we have dark color, but should present a high base saturation, and we don't have a high base saturation. So it's not a molic horizon, and it's not a churnic horizon too, because it also should present a high base saturation and a high content of calcium carbonate. And we don't have the both. Why we don't have a high content of calcium carbonate? Because we have a low content of calcium and the pH it's also low. If we present a high content of calcium carbonate, the pH should be high, okay? So if in this horizon we present a low content of calcium and a low pH, it's not a churnic or molic horizons, okay? Next one, it's an umbric horizon that present moderate or high organic carbons. Okay, we have this. It's thick. Okay, it's 35 centimeters. It's dark. Okay, we have dark colors and should present a low base saturation. And we have a low base saturation. It's just 3%. So let's check. We have material that present paths that present aggregates. We have a strong structure, so we follow. We should present at least 0.6% of soil organic carbon. Okay, we have much more than that. We have, let's check again, we have 18% of organic carbon, so we check again. We have dark colors in the material with low values and a low chroma. We have a dark color. We have a texture of loam sand or coarser, and we have sandy clay loam, so it's coarser. So we follow this criteria too. Should present dark colors like here. We also following this. We follow the content of organic carbon, so it's okay. And it should present a higher content of organic carbon in comparison with the parent material. In this case, we don't have the information of the parent material, so we just skip this information, okay? But if I present you, we could compare, and the base saturation should be low. So we should present a base saturation lower than half, and we have just 3%. So we follow all the criteria except by this information, because I did not mention the organic carbon content of the parent material in this case, okay? So it follows all the criteria, so it's an umbric horizon. I think that we have this. Oh, we have to present at least 20 centimeters, because not over the rock, we don't have this information, and we follow this criteria too, because we have 35 centimeters of thickness, okay? So the exercise to follow all the criteria for the umbric horizon, and it's umbric horizon. So the first one was a Arctic horizon, and the second one is the umbric horizon. Okay. Do you have any doubt? That's something that one will ask?
I was able
No?
to get the second one. No doubt, I
Okay.
got the second one.
Ah, very good, very good. I'm glad to hear that. Congratulations. Very good.
Thank you.
So let's start now. Oh, no. Here, let's start. Here, okay. Let's start the subsurface diagnostic horizons. And the subsurface horizons, they are very important to us, because in general, we classify soils following its presence or not. So if we have an Argic horizon or a Phthalic horizon or a Cambic horizon or Gleic properties in the subsurface, we use this information to classify soil, okay? So,
Pedro,
or,
sorry to interrupt. When you were calculating the cation exchange capacity, the formula that you wrote Base saturation plus. That was the hydrogen plus aluminum.
Yes, yes, we should use it. Okay, let me present here. To calculate the cationic exchange capacity, we should present the sum of bases, okay? That's calcium, magnesium, sodium, and potassium. And we also should sum hydrogen and aluminum because they also neutralize negative charges. Okay, so we should use everything that neutralize charges, okay, to calculate this. I think that someone asked something, just let me check, okay, just a moment. Yeah, oh, it's not an anion exchange. No, because they are cations, they are positive charges. They neutralize negative charge, okay? Let me see in this case, try to think that this is a clay, okay, just a clay particle. So we have something like 0.002 millimeters here. And let's just check this fraction of the clay. So we have something like this. And here we have a lot of negative charges. And these negative charges, they are the CEC. Okay, these negative charges, they are the cationic exchange capacity. Okay, so we should calculate the cationic exchange capacity using all the elements that neutralize charges here, including hydrogen and aluminum. Okay, so we need to include all these elements to calculate this. It's different from sum of bases. The sum of bases, we only include this, 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 and this. So we all include the bases here, but here we should include everyone because we need to know all the charges, all the quantity of charge, of negative charge that we have, okay? So it's why we include here the hydrogen and aluminum, okay? We don't use other elements like phosphorus, or we don't include sulfate, because in this case, they present negative charges. So in this case, they are related to anion exchange. So no, we don't use, we only use positive charge. We only use cations, okay? Because they are related to negative charges, okay?
Okay.
Okay, very good, very good. And talking about the subsurface horizons, as I said, they are very important because when we are describing the star profile, like A, E, B, C, blah, 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 we generally use this and this horizon. And in some cases, we use something like this A and C horizon, and we use this horizon to soil classification. So The subsurface horizon is very important because express specific soil process, soil genesis, and it's why we use it to classify, we use them to classify soil, okay? And they are the subsurface horizon. I write in the wrong way, subsurface, sorry, subsurface diagnostic horizons, okay? And let's see, the first one, I think that's one of the most important. It's why I put it in the first, because it is very important. The Arctic horizon, it's a horizon, let me see, here, that present a higher content of clay in comparison with the with the surface horizon or the overlaying horizon. So here we can split this A horizon and here this E horizon and here this B horizon, and we easily see that the B horizon present different color and probably a different texture in comparison with this E horizon. So this B horizon presents dark colors, a redder color, and probably a higher content of clay. It's a clay-rich horizon in comparison with the overlying horizon. In this case, this E horizon, okay? But we also could compare this B horizon with the A horizon. It's not the case, this case specifically, but we have a lot of cases that we compare the B horizon and the A horizon, the content of clay here and here, okay? And now we have to think. We have the same parent material, they are not different, like we have the same parent material for all horizons and layers in this soil profile, but they present a high difference of clay content. So the A and E horizons, they present lower, very lower content of clay in comparison to B horizon. So B horizon present a distinctly higher clay content. Okay, this is the Arctic horizon. JJ, why this is important to us? It's very interesting to understand. It's very important and interesting to understand that this kind of diagnostic horizon present different soil properties in comparison with the overlying horizons. For example, in this case, we have a sandy A and E horizon, and we have a clay B horizon. So when it starts to rain, the rain could easily and fastly penetrate through this horizon because we have a sandy texture with a lot of large voids that helps, that favor the penetration, the infiltration of water. But when water found, achieve this clay horizon, the voids, the quantity of voids is not so high, and the size of voids are very smaller. So the penetration of water here is not so fast, and water could start to be stagnant here. Water start to be stagnant, and we start to accumulate water in a higher position to the water table. So water table, it's very deeply, it's like 1 or 2 centimeters below this, but we have the accumulation of water because the porosity of this horizon, it's very low, and the penetration of water, it's slower than these two horizons. Okay, so the presence of our Argec horizon should always remember us that we have differences of hydric properties. So the penetration of water is different between the horizons. We could have a faster penetration and a slower penetration depending on the clay content of these horizons. And the Argec horizon present differences of hydraulic conductivity, how fast the water could penetrate through the horizons. Okay, other soil property that usually can see the difference is the CEC. In this case, we have a sand texture, and in these cases, generally the CEC is very low because sand did not present a high specific surface, so couldn't hold a lot of bases or even acid, okay? But here, with a lot of clay, we could present a high CEC and a high capacity of exchange the cations, okay? So we have a difference of chemical and physical soil properties in the same soil profile. So we shouldn't think that a soil that presents an Argec horizon has a specific behavior, a same behavior through all the soil profile. No, we should understand that we have here a horizon or some horizons that present a specific soil properties, and here the Argec horizon present other ones. They could present differences of physical and chemical soil properties. Okay, so it's why the Argec horizon is so important. It tells us a lot about how could I use the soil and how shouldn't use the soil. Okay. The increase of clay content in the subsurface horizon could be related to the clay eluviation. What is clay eluviation, JJ? The clay eluviation is the migration of clay from the surface to the subsurface horizon. Okay, so clay could migrate, could be lifted from the surface and concentrate in subsurface horizon. How clay could migrate through soil profile? Very easily in wet environments. If we have a wet climate with a high quantity of rainfall, the water could penetrate through the soil. And when water penetrates through the soil, water could migrate and brings clay from the surface to the subsurface horizon. Okay, how the water could do this? When we have in the surface horizon pads or aggregates that could shrink and shell daily, if they usually present a high content of expensive materials, expensive minerals, they could shrink and shrivel, shrink and shrivel. And the shrinking and shriveling process, this changing of the size of the pads, start to broke the pads, broke the aggregates, and release clay. So clay, once is released by the pad, once it's not inside the aggregate, it could migrate with water, because clay, it's a very thin and light particle. So could migrate through the voids, through the pores, and concentrate in the subsurface horizon. So we start to induce a change of the texture between the horizons. The surface horizon, that it's always losing material, clay particles, thin materials, and a subsurface horizon that is always receiving this material, receiving the clay and accumulating and concentrating clay particles. And so this horizon gets sandy texture, and this horizon presents a clay texture because of the clay eluviation, because water migrates through the soil profile and brings clay. Okay? It's very common process that we can see in the tropics. It's very, very common process. Okay? And it's very important to understand why water generally concentrate clay in the B horizon, because if you think in this way, we have the A horizon, we have the B horizon, and below we have the C or even the R layer. So we have rock. So water could migrate here very easily, but when water found the sea horizon or even the rock, water stopped to migrate. So if water stops, the clay also stops, and clay start to accumulate in the B horizon and increase the clay content of the B horizon. Okay? So migration of water, it's also related to migration of clay particles, and this could change the texture of the surface and subsurface horizon, producing a clay-rich subsurface horizon. Okay?
Okay.
Okay, very good. Other process that is very important, it's the clay elutriation. What is clay elutriation? It's also the migration of clay. Again, clay is just moving on, but now clay is not migration, it's not migrating from the surface to the subsurface, but now the clay is moving in a lateral direction. How can we see do in this field of JJ? It's very easy. Think in this case, we have here.
Okay, sorry, JJ, what are you defining now? Clear what?
Clay elutriation is the losing of clay, is the migration of clay. But now clay is not moving from the surface to the subsurface, but now clay is being losing laterally. Okay, they have a lateral direction. I will show you now. Okay, think in this case that we have the A and the B horizon, and in this case we didn't have a wet climate but a dry climate. So water, the rainfall, it's raining in a very few days only specific days, and it's a lot of water at the same time. We have a heavy rain that fall at the same time, and water couldn't penetrate through the soil because it's a lot of water, and water start to migrate laterally by runoff. Okay, so we have runoff because we have intense rainfall, and soil couldn't penetrate, couldn't absorb all the water that's falling. Okay, no problem. But when we have a dry climate, we generally didn't have a dense vegetation cover, but we have an open vegetation cover. So when we have open vegetation cover, we have a lot of soil that is exposed. And when we have a lot of soil that is exposed, we could register the splash effect. What is the splash effect? Is the effect of a rainfall, a raindrop that achieves the soil profile and break the aggregate that's here, because this raindrop is very fast and have a small size, a small area of impact. So the impact, it's always breaking the aggregates, the pads, so they are losing particles, solid particles, and they broke some sandy particles, some clay, or some silt particles, and some sand particles. Oh, I'm sorry, some sand particles, I'm sorry, some silt particles, and some clay particles. And as we have the runoff could bring the clay, could leave the clay, and clay's always migrating by the effect of the runoff. And now we have a surface horizon that's losing the clay, so it starts to increase the silt and sand contents in the surface horizon, so it start to get sand or present a sandy texture, and the clay, it's always being losing by the effect of runoff. So in this case, we have an A horizon that only lose clay by the effect of the runoff. Water is not migrating and leaving and bringing clay from the A to the B horizon. The clay is just living on by the runoff, okay? And we create a horizon that presents a low content of clay particles. And here we didn't lose clay because we didn't suffer the effect, the splash effect. So the clay content, it's okay. We are not losing it. And if we have a lot of weathering, we could create a lot of clay particles here. We could present a clay B or a clay-rich B horizon below a sandy A horizon. So the loss of clay by runoff, it's also related to the creation of an argic horizon. Okay? They both are arctic horizon. The arctic horizon that's created by migration of clay from the surface to the subsurface horizon, and that horizon, the B horizon, that didn't lose or gain clay, but is related to a horizon that's losing clay from the landscape. So in this area, we have here an A horizon that's losing clay by the effect of runoff, and this clay start to concentrate in another area, like a depression or a terrace or a alluvial area. It's not a problem, but this A horizon start to get sandy, and this horizon, it's clay rich because the weathering increase the content of clay here. And now we have a horizon that presents a higher content of clay in comparison to the overlaying or horizon. Okay? We also could present an arctic horizon that's related to clay formation. So if we present a horizon and below a B horizon, in here we have intense weathering, and this intense weathering create a clay horizon. And here in the A horizon, we don't have so deeply weathering, so the texture here is something like loamy or sandy or silt. But here we have a clay texture. So the formation, the weathering of the primary minerals and creation of kaolinites, smectite, light, the secondary minerals could also create the arctic horizon. Okay? So it's not the migration of clay, but also the formation of clay could form an arctic horizon. And of course, the destruction of clay also could create an arctic horizon. In some regions, we have intense destruction of clay in the surface. And in these cases, the surface horizon presents a sandy texture, and the subsurface horizon presents a clay texture. So even the destruction of clay could create an arctic horizon. How could we see the clay destruction of the surface horizon, JJ? It's very common in some areas, but they should present an acidic pH, a very low pH. In this case, the hydrogen, that's very rich because we have an acidic pH, we have a lot of hydrogen, start to dissolve, to destroy the clay fraction in the surface, because the low pH destroy clay. So we start to lose clay, not by migration, but a chemical destruction of these clays. And we are losing clay and getting sandy. So we present an arctic horizon because we have a clayic horizon below an sandy material. Okay? We also can see the upward movement of coarse bodies when we have some sand and grave materials here, and they migrate from the subsurface to the surface horizons. And this upward movement generally occurs in materials that present a high content of expensive clays. So these clays that could suffer shrinking and swelling, that could change its volume, they could compress coarse materials, and these coarse materials are upwelling, so they start to migrate from the subsurface to surface and concentrate here and produce a horizon in the surface that present a high content of gravels and sand. Okay? We also could see this object horizon in soils related to biological activity, because biological activity mix the material, but they generally select the material, and they generally select the material to increase the clay content in the subsurface, because clay help them to keep a hot and wet site here. Like the termites, they select the clay fraction, and because they didn't select the coarse fractions start to accumulate here, and they generally see a concentration of clay, of coarse materials, or sand fraction here, and a concentration of clay fraction in the subsurface horizon. Okay? And of course, we can see more than one of these processes at the same time. We can see the clay eluviation and elutriation at the same time, or we can see the clay formation and eluviation at the same time. We don't need to follow just one of these options. We can see all of them acting at the same time. Okay?
Okay.
Okay. Now we have the diagnostic criteria for identify this object horizon. We see this in the next class because it's a lot of information, and we need to calculate some values to check if they follow all these criteria, okay? So we stop here just discussing about how we could identify the object horizon. The definition of it is a horizon that is in subsurface that present a higher content of clay in comparison with the overlying material, overlying horizon. Okay, this is very important to remember when we start to describe the definition and the criteria of the object horizon. Okay? Do you have any question?
I'm okay, JJ.
Okay. Okay, good. So, here, okay. So, I ask you to keep reading the material. So in the next class, we start to discuss about the criteria of the object horizon and other soil diagnostic horizons. Okay?
Okay.
So I will share another exercise. So you try to classify the surface diagnostic horizon, okay, again, and the next class we could discuss about this exercise. Okay. So have a good night. See you. Bye-bye.
Bye-bye, JJ.
Bye bye, Gigi.